All right, so 2.2, we're going to be talking about similar things to 2.1, but this time we're dealing with quantitative data. The bulk of this chapter is going to be dealing with the frequency distribution of quantitative data and how we turn those into histograms. Then towards the end of it, we'll get into some other types of displays and the shapes of graphs and what those tell us. So first, start out with our frequency distribution. This time, instead of talking about categories, we call those classes. And when we start, we're going to be dealing with discrete data with a small range of values. So again, discrete data means that there's a jump from one possible data point to the next. Number of points in a basketball game, number of desks in a classroom, those types of things are discrete data sets. And so that's what we're going to start with, and with a small range of values. If our data is continuous or the range of the data gets to be too big, we have to switch to a different type of frequency distribution. So for the first part, instead of categories, we have classes, and each value for our data point is going to be its own class. And then after that, it should look very similar to what we had for qualitative data. We have our class, we have our frequency, then we have our relative frequency. And this time, instead of a percent, we get our cumulative frequency. And sometimes you have both a cumulative frequency and a cumulative relative frequency. Cumulative simply means continuing or adding up. So the further we get down, we just keep adding the new frequency to the sum of the old frequencies and continuously adding those up. And then we have some definitions in here for cumulative, relative, and cumulative frequency. And then we'll get to our first example. So again, as we're going through this, pause, attempt the problem, and then unpause, and we will do it as a class. So this setup for the backstory for our first problem, we have patients that are recovering from a knee replacement surgery. They were asked how many days they took narcotics for pain management, and the following data represents their answers. We are to construct a frequency distribution. So we go through and we see all of the possible data values. So we look for the lowest, we look for the highest. So lowest appears to be 2 and the highest appears to be 6. So we need to make sure that we contain all possible values between 2 and 6. So that means 2, 3, 4, 5, and 6. Even if there was a gap, even if, say, no one answered 5 days, we would still have to have a 5 represented in there because it is a possible answer, even if no one gave it. We'll get a little bit more into that when we start dealing with continuous data. So 2, 3, 4, 5, 6, and then we go through and count their frequencies. So our frequency for 2 is there are 4 2s, 4 3s, 4 4s, 2 5s, and a single 6. Then we go through and we do the relative frequency. So relative frequency, then we count first. So 8, 12, 14, 15. So I got a total of 15. And then we go up and we count how many data points there were. And there were a total of 15, which is good. Then we do our relative frequencies by dividing our frequency by the total. And we get 0.267 for the first 3, 0.133, and then 0.067. So that's our relative frequency. Next, we're going to look at the cumulative frequency and cumulative relative frequency. Cumulative frequency is essentially a less than or equal to operation. So how many patients took it for 2 or fewer days? Well, 4 people took it for 2 and no one took it for less than 2 days. Next cumulative frequency is how many people took it for 3 or fewer days? Well, 4 people took it for 3, 4 people took it for 2. So a total of 8 people took it for 3 or fewer days. Next one would be 4 or less. That's 12, then 14, then 15. And the last cumulative frequency number should be the total number of data points in your data set. So 15. Next, for cumulative relative frequency, it's the same idea, except this time we're using our relative frequencies instead of our regular frequencies. So 0.267, and then 0.267 plus 0.267, or you can use 8 divided by 15, which is our cumulative frequency divided by the total. Those should give you the same number with rounding error included. So depending on where you round, you may get a slightly different answer, but they should be extremely close. Then 0.8, 0.933, and your final relative cumulative frequency should always be 1, because your final cumulative frequency should be equal to the total. And so that should always come out to be 1. All right. And that is how we create our frequency distribution for quantitative data. Next, constructing a histogram. Now, a histogram is going to look an awful lot like a vertical bar graph. There are a few key differences. They're listed in the how to construct. First, your x-axis is always going to be the value of the class. Your classes are always numbers, so your x-axis is always numbers. In fact, it's not just numbers. Your x-axis is a real number line. A real number line. So much like if you remember in kindergarten, if you were in a math class, or maybe in elementary school, around the top of the classroom where the wall meets the ceiling, sometimes teachers would have a number line. It starts at 0 and then goes 1, 2, 3, 4, 5, and then -1, -2, -3. That's a real number line. Once you start, you have to include every possible number until you stop. That's what our x-axis is. We start with a number. It does not have to be 0. In this case, the frequency distribution that we just made, in fact, it's not 0. It's going to start at 2. But once we start at 2, we can't skip any numbers until we get to 6. So we have to do 2, 3, 4, 5, 6, and then we can stop. But from once you start until you stop, you have to include all of the numbers. You can't skip anything. And then the other thing is, this number 4 is the big one, and that is the rectangles should touch. Your bars, when you're making a histogram, need to be touching each other. If they don't touch each other, that tells us something about the data set we're looking at. And typically, if we leave a blank space there, we're giving misinformation. And again, there's an example later on where there's supposed to be a gap, and I'll show you that gap and I'll show you why it's there. And then that should make the point of why we don't want it in most cases. So we are going to make 2 different histograms. We are going to make both a frequency and a relative frequency histogram for the number of days. So this is the data set we just created and just used. So you can go down and check to make sure that your answers are the same as this. And then we are going to make a histogram out of both sets. So we're going to make one using frequency and one using relative frequency. All right, let's get to it. Both of these can have the same title as they're describing the same information. The only difference is going to be that y-axis scale. Both of these are going to be the number of days taking pain meds, or the number of days taking pain medication after knee surgery. You get the idea. It's something about that. It's referencing the number of days that you were on pain medication after a knee surgery, whether you mention the knee surgery or not that important, but something to that effect. And then both of these are going to be number of days. And then one of these is going to be frequency. And the other one is going to be relative frequency. Next, I need to come up with my scale. Now, I don't have to start at 0. I don't have to start at 1. If you want to, you can, but you don't have to. So when you don't start at the 0, when you don't start at 0, you put that little break in the graph to show that, hey, this first box isn't going to be the same as the rest of the boxes. It's called that graph break. If you've taken science classes, generally that is taught in those types of classes. But if you don't start at 0, or the gap between your kind of starting line and your first bar is going to be different than everywhere else, you put that graph break in to show that the scale there is different than it is everywhere else. And then I'm going to make here to here, I'm going to put a 2 in the middle, and then a 3, and a 4, a 5, and a 6. And on these here, you see that the rectangle should be touched and should be centered at the classes. So my 2 is going to go from here to here. And then 3 starts where 2 ended and then goes that next box. And notice that that class number, the number of days, is centered underneath each rectangle. And then my possible frequencies go from 1 up to 4. So I'm going to make each 4, and then I have a 5 up there. And again, we want to use as much of that white space as possible. We don't want to shrink everything down if we don't have to. So use as much of it as possible to make it look nice and big so you can tell those small differences if there are. Then that's for 2 days. And if you have colors, you can switch colors between them. Not necessary. That would be 3 days of taking pain medication. That's going to be 4 days. Oh, I meant to switch colors on that. Four days. 5, and then the last one, 6. And so you can tell like that. To make it a little bit more obvious how big those rectangles is, you will often see them either colored in or put in some kind of pattern to make it easier to see where things start and stop. So I'll go in and fill. And there we go. So that is my frequency histogram for the number of days of taking pain medication. And next I'm going to do a relative frequency distribution. And that's going to change the scale that I have. So my scale, I'll put 0.067 there, 0.133. Then up to here will be 0.267. And in the middle is 0.2. And then again, I'm going to set it up in basically the same manner. That's a 2, 3, 4, 5, and 6. And then go through. 2 goes all the way up. And then 3 goes all the way up. And we fill that in. 4 also goes all the way up. Sorry, I'm not sure why my screen keeps unsharing. Four again. So we have 2, 3, 4, 5, and then 6 ends here. And that is my relative frequency. Now, take a look at the shape of those two graphs, and what do you see? You see that those two graphs look the same. The only difference between them is going to be the scale of the y-axis. It does not change the shape. The shape stays the same between frequency and relative frequency. The only change is going to be that y-axis scale. All right. Now we've finished the nice, neat, kind of easy type of data, and we're now going to be moving into how do we handle continuous data? What if we don't have nice, neat whole numbers with a small range? So the thing we're going to talk about next applies in two cases. First, any continuous data. No matter how big or how small our data set is, if we have continuous data, this is what we're going to have to use. And the other case is if we have discrete data, but the range of our data is extremely large. So an example of discrete data. So we've talked about the fact that money is discrete. The smallest increment of money is 1 cent. So money is a discrete data set or a discrete data point. But if we talk about housing prices, the range of houses is massive. You can have houses that are as cheap as $50,000 all the way up to millions of dollars. And because of that, we are unable to make a nice, neat, discrete value of, oh, every housing price gets its own class. And so what we have to do is come up with a class that contains more than one width, or a width of more than one. So instead of just going from 2 to 3, we're going to have to start dealing with classes that contain multiple values. And so when you do that, you have to create an upper and a lower class limit. The lower limit is when our class starts. Our upper limit is when our class ends. You can think of these classes, instead of just like a class, you can think of them as a bucket or a bin where you're putting everything that falls within the range. So if we were talking about housing prices, maybe my classes are $25,000 wide. So I say anything that is a housing price between $50,000 and $74,999, I'm going to put all of those into one bucket or one bin. And then I'm going to go from 75,000 to 99,999. I'm going to put all of those into a different bucket. And each of those ranges would be considered a class when we're dealing with continuous data or data that has a large range. And again, that's the lower and the upper class limit. It talks about the smallest data value that can go in and the largest data value that can go in. And then the rest of it is pretty similar. We have our frequency. We can do cumulative frequency, relative frequency. The only part that's new is in this column number 4 here, this midpoint. And the midpoint of our class is going to come in handy when we start dealing with data points and trying to describe our data set from a histogram or from a frequency distribution. And so the midpoint is found by averaging consecutive lower limits. All of the math, not all of the math, most of the math that we're going to do that involves class limits is going to be based off of consecutive lower limits. So it would be this number here and this number here. We go from lower limit to lower limit. And that's how we find midpoints. We go lower limit to lower limit, then divide by 2. Class width is found by subtracting consecutive lower limits. So midpoint, we average lower limits. Class width, we subtract lower limits. When you are creating your frequency distributions, your class widths must be consistent. So I was giving my housing prices, I had to go up by $25,000 each time. I can't go up $25,000 for one class and then go up by $50,000 another class and then back down to 25, because that changing the width is going to skew the results and give us bad data. So we need to make sure that our class width is consistent. Once we find it, we have to keep that same width throughout the entire process. All right, so here, let's find the width and then find the midpoint of our first class. So starting off, in order to find class width is found by subtracting consecutive lower limits. So I'm going to start off with our first and second lower limit. So that means I'm going to take 31 minus 24, and I'm going to get 7. So my class width is 7. Theoretically, that means there are essentially 7 different answers that will get put into that first bucket, that first bin, that first class. Now, you may think of that, look at that and go, 24 to 30, there's only 6 numbers that I'll put in there. But if you count it, let's count it. So 24 will be the first answer that we would put into that class. So 24, 25, 26, 27, 28, 29, 30. If you counted with me, you'll be holding up 7 fingers. That means there are 7 different answers that get put into that bucket, and that's what our class width is telling us. Our class width says how many different answers get put into each of these buckets. Now, the next step is that needs to be the same for the entire frequency distribution. So we can double check and make sure our next class also has a class width of the same thing. So we do 38 minus 31, and that gives us 7. So we've checked our first 2 are accurate, and we can assume that the rest of them are as well. When you're making them, you don't get to assume. You actually have to create classes that have the same width. So you'll need to double check all of them. But in this case, it's safe to assume that if the first 2 are, we can assume the rest are. Next, what is the midpoint of the first class? Again, it is all based on consecutive lower limits. So we did 31 minus 24 for our class width. We're going to do 24 plus 31 divided by 2 for the midpoint. So 24 plus 31 gives us 55 divided by 2. That tells me my midpoint for this class, that first class, is 27.5. And then you would do that same process for each class in order to find the class width or the class midpoint. Now, because the class width is consistent, you're going to notice that class width shows up in a lot of different places. We find it by subtracting consecutive lower limits, but you could also do it by subtracting consecutive upper limits. So that means if instead of 31 minus 24, I did 37 minus 30, I also get 7. Another place it shows up is in the difference between midpoints. So once you find your first midpoint, so this would be midpoint 1. If I wanted to find midpoint 2, I could either do that same averaging process with the next set of lower limits. So I would do 31 plus 38 divided by 2, or I can simply add 7, which is my class width, and come up with my next class midpoint. And again, you can double check to make sure that's correct by adding 31 plus 38 divided by 2, and you get 34.5. So that class width pattern shows up in multiple places, and you can use that to your benefit to make your life a little bit easier. All right, next, how do we find the class width we should use? So if you're given your classes, it's easy enough to find. You simply do subtraction. But what if you're just given the raw data and you have to create your own classes? How can you figure out how big each class should be? This is the process for that. You start by finding your range. So that's the highest number minus the lowest number. That tells you how much data, how many different data points you have. Then you choose the number of classes you're going to create. In our cases, I will give you that answer. So I'll tell you how many classes you're going to create, or your homework will tell you. That's not up to you. However, when you're doing your own research, that's something that you get to choose. But in our case, it will be given to you. Then in order to find your width, you take the range and you divide it by the number of classes that you're going to have. And then once you've done that, you round up to the next whole number. So if you've done your division and you get 2.1 is your class width, you round that up to 3. If you get 2.01, you round that up to 3. No matter what your number is when you do your division, round up to the next whole number. So here's our first example. Suppose the lowest value for the high temperature of all 50 states is 100. So this example it went through, it collected 50 low temperatures. So the lowest temperature, the lowest value of a high temperature. So it collected the highest temperature of all 50 states, and the lowest of that high temperature was 100 degrees. And then the highest of the high temperatures was 134 degrees. And we want to split our 50 points of data up into 7 classes. So our first step is to find the range. So that is high minus low, so 134 minus 100. Our range is 34. To find our width, we take our range and divide it by the number of classes. So 34 divided by, we want 7 classes, and this comes up with 4.86. So that means our class width is going to be 5. Now, we would normally round 4.86 up to 5, so that makes sense. But even if we had gotten 4.001, we would still round that up to 5. Always round up, no matter what that number is, round it up to that next closest number. When you're creating classes, you have to make sure that you create classes that are mutually exclusive, meaning every single data point has one and exactly one, only one class or bin that it fits into. This first example is a poor setup because if someone is age 20, do you put a 20-year-old here or do you put a 20-year-old there? It's not clear, so this is a poor way to write your class widths. On the right-hand side, you get a better example. It goes from 10 to 20, then 21 to 31, 32 to 42. There's no age where you're not sure where to put someone. Now, when you go online or if you take a stats class in college again, the way you write your classes differs from book to book to book. I've taken 3 stats classes, and then this one I teach. All 4 of those classes had a slightly different way of talking about classes and how they've written them. So be aware of that. If you go and look, you will see something like 10 to 20 and then 21 to 31. Sometimes you'll see classes written as like 10 to less than 20 and then 20 to less than 30. That's another common way of writing that. I don't care how you write it. This is how your book is going to do it. So that's the way I'm going to teach. If you go on to take another class, just be aware that there are different ways to write it. Or if you happen to go on the internet to look for some help, there's a chance that the website you look at is going to be different than this book. So just be aware of that and understand that it's not good, it's not bad, it's just a different way of doing it. And both ways are perfectly acceptable. Next, the classes must be continuous. Even if there's no data in a particular class, you can't skip values. So here we start at 10 and we go all the way up to 53, and every possible age is incorporated in those classes. Even if there wasn't a 32 or 33-year-old, you could not make this class something like 34 to 42 and just skip the possibility of having a 32 or 33-year-old. You have to make sure that you include all possible outcomes in your classes, or you get bad data. So that's not good. You have to make sure once you start, just like a number line, you have to include every possible outcome until you reach your ending point. And the classes must be exhaustive. That goes with that continuous part. Every single data point in your raw data set must show up in your class. If your highest value is 102, you can't stop a class at 100. You have to make sure it goes to at least 102, if not higher. It can go higher if you want. If you have a data point of 101, if you have to, based on your class width, go up to 105 or 110, that's okay. But you have to go to at least your largest data point, if not a little bit higher, depending on how your class widths work out. All right. Now we're going to go through and kind of do this whole process. So we have a data set. Our data set is the average quantitative GRE score for the top 30 graduate schools of engineering. So GRE is the graduation something exam. It's essentially the ACT or SAT of getting into grad school. So if you try and get your master's or your doctorate after you've gotten your bachelor's degree, a lot of colleges will make you take this GRE exam to see if you qualify to get into their program. Other professions have similar things, like there's the LSAT for lawyers, there's the MCAT for doctors, medical doctors that are trying to get into a med school. They take the MCAT to see how well they do in certain things. The LSAT is if you're trying to get into a law school. The GRE is just a more general version of that test. So first thing we have to do, we're looking at 6 classes. So I'm going to create 6 classes. That's how many I want. First step, have to find the highest, have to find the lowest so we can figure out the range of values I need to cover. So we go through. Looks like 780 is the highest. Trying to find the lowest. Looks like it is 746. So we subtract those, 780 minus 746, and that gives us a range of 34. We're going to have 6 classes because that's what it tells us. And that means we have a class width of 34 divided by 6. Which gets us to 6. Next, we have to figure out where are we going to start. So where we start is typically a nice, neat number that is at least close to our lower limit. For the purposes of our class, we are always going to use the lower limit. Whatever our lowest value is, that's where we start. So in this case, our first lower limit is 746. To find our second lower limit, that means we take our first lower limit plus our class width. So that is 746 plus 6, and that gives me my next lower limit as 752. So there's a difference of 6 between my consecutive lower limits. Now to find my first upper limit, how do I find that? So essentially what I have on this page here, I know that this is 746 to something, and this is 752 to something. What is that something? Well, that something is going to be one less than the next lower limit. So this is going to be 751. Oh my goodness. $751. All right, once we have started that, please go ahead and fill out this entire frequency distribution. So come up with the rest of the class limits, upper and lower limit for each class, the frequency, the relative frequency, and our cumulative frequency, and then unpause, and you can check to see if you did that correctly. All right, so let's go, and I'm going to first finish filling out all of my lower limits. So each of these has a difference of 6. So add 6 to each of these to get that next one. And then once I have my first upper limit, I can just add 6 to all of those to get to that next upper limit. Or subtract 1 from the next lower limit. The tricky thing is here, people say, I don't have a next lower limit to subtract 1 from. How do I know what that upper limit needs to be? Two different ways, essentially the same thing. First, you can just keep adding your class width to your upper class limits all the way down. Second, you can figure out if we had one additional class, what would the lower limit of that class be? And then subtract 1 from that. So either way, you're coming up with that same answer, which is 781. If I had one more class down here, it would be 782. And then so I'd subtract 1. And so two different ways of getting that final upper class limit. All right, so I have my limits. Now for my frequencies, we go through, we count to see how many of those scores fit into each of our classes. And we end up with 4, 4, 7, 6, 6, and 3. And that is a total of 30 different values. So up here, I'm going to count to make sure I have 30 different data points. So I go down 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. 5 times 6 equals 30. I have 30 data points in my data set. I counted 30. So my frequencies and my data set match up. That is a good, quick, easy check to make sure I'm off on the right foot. Next, I'm going to divide all of my frequencies by 30 to come up with my relative frequencies. So that would be 40 divided by 30. 7 divided by 30. Six divided by 30. 0.2, 0.2, and then 0.1. Next, I need to find my midpoint. So again, when you're finding your midpoint, we're using consecutive lower limits. So consecutive lower limits. 746 plus 752 divided by 2. That will give me my midpoint. 746 plus 752 divided by 2. Midpoint, 749. Now, to find the rest of my midpoints, two different ways. I can keep doing that same thing of averaging consecutive lower limits, or I can use my class width. And I can just keep adding 6 to that. So, find my next one, add 6, it's 755. Plus 6 again, 761. 767. 773. And my last one, 779. And again, you can go ahead and double check to make sure that you're getting the correct midpoints by doing the averaging of consecutive lower limits if you want. And then the last thing is cumulative frequency. So again, that's where I simply add up my frequencies as it is a less than or equal to. So starts with 4, and then 4 plus 4 is 8. 8 plus 7, 15. 15 plus 6, 21. 21 plus 6, 27. And then 27 plus 3 is 30. And as always, your last row in cumulative frequency needs to equal the total frequency. And that is how we create a continuous or large range of discrete value frequency distribution. All right. Next, pause this video, and we are going to do that same process with this data set where we're dealing with the tax rate of cigarettes in different states. So go ahead and start that and then unpause, and we will talk about where each of those answers comes from. All right, so it gives us some key information that's going to help us fill this chart in. If you read that kind of setup piece of it, it says first, having a lower class limit of 0. So that's our first class has a 0 start, and then it says our class width is 0.5. So you go from 0 as our first class, lower class limit, then 0.5 is our next lower class limit, then 1, 1.5, 2, 2.5, all the way down until we reach an upper limit. And we go through, and if 0.5 is our lower limit, we go as many decimals out as is in our raw data. So you can look at some of these, and we have 2 tax rates that go out to 3 decimals. So that means when we have upper and lower class limits, we need to go out at least 3 decimals. So that's why our upper class limit is 0.499 and then 0.999. If our taxes were whole numbers, then our lower limits would be whole numbers, or our upper limits would be whole numbers. If it went out 2 decimals, then we need to go out 2 decimals when we do with our class limits. But since it's 3, we need to go out at least 3 decimals. And then we have our frequencies, which we find by simply counting, add them up. There are 51 data points, and so we need our frequencies to add up to 51. And then our relative frequencies and our cumulative frequencies are there as well. And if you want to double check to make sure that this is correct or that yours is correct, on the next page, we have that same frequency distribution with frequency and relative frequency included, but no cumulative. Next, we are going to create a histogram for our continuous data. Couple things you need to remember. Number 2, on the x-axis, we put the values of the lower class limits. That's the only thing that shows up on the x-axis. Lower class limits. That's it. Next, the y-axis is either our frequency or relative frequency. And then we draw our rectangles starting with the lower class limit and ending at the next lower class limit. And the height depends on the height of those certain classes. So take a second and attempt to come up with our histogram. Pause it, check. Again, make sure we label X and Y axis and we have a title of our graph. So pause, take a second, and then we will talk about it as a class. All right, and this is roughly what your graph should look like. I don't know what happened here. This should say number of states. Number of states / District of Columbia. Now, we go through, we have a title, so cigarette tax rate by state. We have an x-axis, that is the percent of that tax rate, and then the y-axis is talking about the number of states that have or fall into each of those categories. We start with 0 and we go to 0.5. Again, pay attention to that x-axis. That is what your x-axis needs to look like. If it doesn't look like that, then you didn't do it right. Make sure whenever you have a continuous data set, it looks like that. Now, the other thing I said is you need to make sure that your rectangles are touching. In this case, they're not all touching. And when I said that, I said it tells us a piece of information. The fact that we don't have a rectangle between 3.5 and 4 tells me that no states have a tax rate that falls into that class. That is a piece of information. So anytime you have a gap between rectangles in a histogram, you are saying that there's a class and nothing exists in that class. You're giving information. And most of the time, if you put a gap between your rectangles, you're not doing it to convey that piece of information. So that's why the rectangles must touch. So be careful with that. That is one of the most common mistakes, is people forgetting to make sure that those rectangles on their histogram touch. If they don't touch, that's telling us a piece of information. And if we're not trying to say that piece of information, we don't want to put it out there. Next, how would the graph change if we wanted to use relative frequency? There's only one thing that would change. The only thing that would change is the scale on the y-axis. I don't know why that's not working. Y-axis. And half the letters disappeared. Cool. All right, so that is continuous data, discrete data, histograms. Now we're going to go into some lesser used types, still not obscure, but definitely not the most common ones. We're going to deal with stem and leaf, dot plots, and then get into some shapes of data. So stem and leaf plot. Again, you've probably seen these before. The first thing you have to do before you make a stem and leaf plot is you have to organize your data. You have to sort it from highest to lowest or lowest to highest. Doesn't really matter the order. You just need to sort that data first. Each number is going to be represented by a stem and a leaf. Your leaf consists of exactly one number and only one number, which is why when we go through and we create our stem and leaf graph, we don't have any commas on the leaf side. That's a common mistake, is people either put decimals or they put commas in that leaf portion, and you don't put anything except numbers in that leaf portion. The stems go on the left-hand side of your line. They go from smallest at the top to largest at the bottom. And then the leaves go smallest closest to the line and largest further off to the right. So let's begin. So here we see we have we have 3 different stems. Again, the leaf is always that last digit. So everything before the last digit is going to give us a different stem. We have 3 different stems, but it goes from 12 to 15. So my question is this acceptable? Is that what a real number looks like? A real number line? No, it is not. And just like with histograms, anytime we're dealing with quantitative data, we have to treat it like it's a real number line. So once we start at 12, we have to go 12, 13, 14, 15. And then we just leave 14 blank, representing the fact that there are no leaves for 14. So for 12, we have 1 leaf of 5, 13, 6 and 6, and then 15 is 7. Now, after we've done this, every stem and leaf plot needs a key. You have to have a key to tell us how to rebuild the data from our stem and leaf plot. What does 12 bar 5 equal? Is it 125? In this case, it's not. It is 12.5. And because we make this key, and you have to make a key, you do not put decimal points in your stem and leaf plot. All right. Do these next 2 on your own, and then come back and we will go over them and make sure that you got them right. All right, for this next one, it looks like we have 3 different stems. We have 1, 2, and 3. And then again, we have to go in order. So I have 0, 1, and 3. So my leaves are going to be 0, 1, and 3. Then I have 1, 1, 9, and 9. So 1, 1, 9, 9. And then 1 and 6. 1 and 6. And that's my stem and leaf plot. And then a key that tells me, okay, if I have 1 bar 1, that's equal to 11. And you have to include that. Now, some of the benefits of a stem and leaf plot is it keeps the fidelity of the raw data. If I have a stem and leaf plot, I can reconstruct data point for data point my original raw data set. I can rebuild all 9 data points from this stem and leaf plot, which is nice. I can't do that with a histogram. If I go back to my histogram and I want to look at this raw data and I say, oh, I have 4 values between 746 and 751. Do I know what those 4 points are? I don't. I lose the fidelity of the data when I create a histogram, which is a downside of a histogram. However, the downside of keeping that fidelity, being able to reconstruct the entire data set, is that imagine instead of 9 data points, this raw data set was 1,000 data points. Then it becomes cumbersome to make a stem and leaf plot, because that means I would have 1,000 leaves. And 1,000 leaves makes it almost as unlegible as just looking at the raw data itself. So when you start getting large amounts of data, that's when a histogram becomes more and more important, or using our frequency distribution in classes becomes more and more helpful, because it consolidates some of that. It makes it easier for humans to look at and kind of understand what's going on. If you just had a stem and leaf plot that had thousands of leaves, you can't really look at it. It's overwhelming. All right, last stem and leaf. Again, the only value that can be on the leaf side of things is the very final digit. So that means our stem is going to be 32, 33, and 34. And then we put a 5 and a 7, put an 8, and put a 1. And then we make our key that says, okay, 32 bar 5 is equal to 325. Split stems aren't used often. A split stem is similar to a side-by-side bar graph. They can compare two different populations of things. You might see average age of teachers, and then in the middle is going to be the stem. So let's say if we're talking about average age, it would be like 2, 3, 4, 5, 6 for someone in their 20s, 30s, 40s, 50s, 60s. And then going off in one direction, you would have male teachers, and going off in the other direction, you'd have female teachers. And then you could see, oh, it looks like the younger teachers are skewed towards female, the older teachers are skewed towards male. But you could compare things like that. If you're looking at the age of teachers in a school or the age of math teachers in a particular building, you could set it up like that where males go on one side and females go on the other side, and do that as a comparison. It's not used commonly, but it is something you'll see in non-scientific papers. So if you're looking at magazines or things that are built more for entertainment than they are for scientific integrity, you'll see that type of thing. Next, we're going to do dot plots. Again, dot plots not very common in scientific research. You might see them in magazines and stuff like that. It's essentially a histogram, but without rectangles. You have dots instead of rectangles. So here, this is that same data we had about knee pain, but now we're going to go and we're going to go 2, 3, 4, 5, 6, and then you put a dot above 2 every time you see the occurrence of a 2. So we had 4 2s up here. We have 1, 2, 3, 4. So I'll put 1, 2, 3, 4 dots. And then we go to 3s, and there's 4 3s. So 1, 2, 3, 4. 1, 2, 3, 4. There were 2 5s and 1 6. And then again, because we actually have a kind of a backstory for this data set, we would want to make sure we include a title. So days of pain meds. This would be number of days. And this would be our frequency. Now, we do not need a scale on the y-axis because each dot represents one observation. Now, if a dot didn't represent an observation, maybe it represented 10,000 because we had a much larger population we were pulling from, then you'd want to make a key that says, hey, 1 dot equals 10,000 people, something like that. All right. Next, we're going to talk about kind of shapes of distributions. And there are 4 shapes that we're going to talk about briefly here. We get more in depth in a couple of them later on in the semester. The first one is bell-shaped. It is also referred to as the normal curve. It is a symmetric curve with one peak in the center. So the peak is in the middle. The left side and the right side of that look the same. You have a uniform distribution. Uniform means that it is a rectangle. The top of all of it is the exact same. When we get into our probability, that's what our graphs look like. This is a good example of a randomized experiment. So like rolling a dice is a uniform distribution. The probability of rolling a 1 is the same as rolling a 2, is the same as rolling a 3 or 4 or 5 or 6. And so that gives you a uniform distribution. If you're talking about the probability of getting a particular card, every card has a 1 in 52 chance of being dealt next. And so that is also a uniform distribution. So a lot of those casino games, gambling games, those types of games of chance have uniform distributions. And then we have skewed. So there's two different types of skewed, skewed left and skewed right. The direction of the skew is based off of the tail. The tail of the graph is what is skewing our data. And so skewed left means the tail points off to the left. You may also see skewed left data look like this if you have a nice smooth curve. And again, the tail points in the direction. Skewed left data often happens when you have a artificial cap on whatever you're talking about. So grades are typically skewed left because there's an artificial cap. The highest grade you can get on a test is 100%. So even if we talk about the 5 smartest kids, even if there's a clear distinction between the smartest and the 5th smartest kid in the class, they can both get 100%. So there's that artificial cap where all you can do is get every answer correct, which if multiple people do that, does not allow you to distinguish between everyone that gets 100%. So there's an artificial cap, and most people are going to get a 70% or better. Most people are going to pass most of your tests. But you'll have a few kids, maybe they didn't study, maybe something happened, maybe they're in the wrong class, but you'll have some students that get significantly less than that 70%, and that's going to skew your graph, your data, your distribution to the left. So if you have a kid that didn't study, didn't care, gets a 10%, that's going to pull your class average way down to the left because of how far away it is from everything else. Then you have skewed right data. Again, you may see that look a smooth curve like that. Things that don't have an artificial cap. Typically, things involving money are going to be skewed right. The bulk of things are going to be in one area, and then you have outliers that are way, way above that kind of average. So things involving money, let's talk about cars. So I would say most cars are probably between 10,000 and maybe on the upper limit, 100,000. I'd say $100,000, still very expensive for a car. But if we want to include most cars, we'd say between $10,000 and $100,000. But there are cars that cost substantially more than $100,000. There are cars that cost millions of dollars, either supercars like McLaren F1s, or you get your Lamborghinis, things like that, or like classic cars that cost millions of dollars, or custom cars that cost millions of dollars that are way, way, way over here in this area that pull all of those averages higher than you would anticipate based on where most cars are. So that's the difference between skewed left and skewed right, and what kind of situation those two situations occur, or what type of graphs those occur in. And then we have some examples here. So we have uniform. This would be skewed left. Again, it's all based off of that tail. Skewed right. This would be our normal curve. And this we didn't really talk about. It is called a bimodal. Mode meaning most common. So when we get into measures of central tendency in chapter 3, we talk about mean, median, and mode. Mode is the most common occurrence. If you have bimodal data, generally that tells you you're not actually looking at one population. So aliens come down to Earth and they want to find the average height of human beings. And so they pick up 1,000 random human beings and they measure all of them for their height. If they then plotted all of that data, it would be bimodal. And the reason it'd be bimodal is because humans are broken up into two distinct kind of subgroups, and those two distinct subgroups have different average heights. And so you'd have one peak at the average height of female, you'd have one peak at the average height of male, and then you would get a bimodal piece of data. So with bimodal data, or if we looked at, if we did that same thing with like lions, and you looked at grabbed lions, and you looked at the average weight of lions, it would be bimodal because lions, male lions, are typically larger than female lions. And so that type of information, when you get bimodal data, typically that means you're actually looking at a population that has two distinct subgroups. And then you may want to do more research to find out what are those subgroups, why do they form, what is that telling me? The last part, if you want to go ahead and answer these three questions. So it's saying, make an imaginary, so you can use whatever data you want, you're just putting dots on there. Make a dot plot that is skewed right. Then you're going to make a histogram that is normal. And then you're going to make a stem and leaf plot that is skewed left. So pause this video, do those three problems, and then come back. All right, so a dot plot that is skewed right. I'm going to start off, I'm just going to go 1, oh, for some reason, my pen is not working.